Alright, hello, I'm Val Browning, and I'm going to be analyzing the third free response question from the 2004 AP Physics exam. Here are some of the required skills that you need to solve this problem, and I'll be going through all of them. Alright, here's a quick review of how to use integral calculus with rotational inertia. For this specific problem, it's a uniform rod of mass m and length L, and it's swinging, and you need to analyze that rotational motion. So the way you analyze rotational motion for a uniform rod is, by using integral calculus, is by looking at this equation on the equation sheet that the inertia for this rotating object is equal to the integral of x squared dm, and on the equation sheet it does say r squared, but for the purposes of this video we're just going to say x. They're both the same thing. And notice that you have two different variables underneath that integral. You have x and you have m. Now you cannot have this underneath an integral or else it's not, like, it's unsolvable. You need to put this dm in terms of x, so you need a dx under here. And to do this, we look at the rod and we say, okay, since this is a uniform rod, we know that the density of the rod is its mass over its length. And we can call this lambda, which is this Greek letter you see right here. Now, for any chunk of the rod, since it's a uniform rod, you know that the mass of the chunk over the length of that small slice is going to also equal lambda, since it's uniform. It has the same density throughout. So you can say that dm for an infinitesimal mass over dx for an infinitesimal length is also equal to lambda. So if you rearrange this equation and you solve for dm, you can say that dm is equal to lambda dx. Now, what we do down here in this integral from the equation sheet is you just basically plug in lambda dx for dm, and that allows you to have a dx in underneath your integral, and you can take lambda out of the integral because it's a constant. It's a constant density for the rod. Okay, so then you can replace lambda with m over L again, and this is the inertia for a uniform rod. Alright, also remember that during rotational motion, x equals r theta, v equals r omega, and a equals r alpha. Just remember those three things for change of variables between linear and rotational velocities, positions, and accelerations. Alright, the parallel axis theorem. The reason we need to analyze inertia using both the parallel axis theorem and the integral calculus method is that it's just two different methods to solve the same problem, and knowing how to do something two different ways is usually always better than knowing how to do it just one way. So the parallel axis theorem states that for an object rotating about an axis not at the center of mass, the inertia about the parallel axis is equal to the inertia about the center of mass plus the mass of the object times the distance squared, and this distance is just the distance between the center of mass and the parallel axis. So we can find the inertia about the center of mass of an object by using the integral of r squared dm, which is just what I showed you, and we called this rx in the previous slide. Or you can just take the sum of the mass and the radius from the center of mass squared for any system, or for any object, extended body. So for this extended body over here, obviously it's going to be pretty hard to calculate the inertia about the center of mass, but since we're just analyzing a two-dimensional rod in this scenario, then it'll be pretty easy. Alright, a review of energy conservation. Energy is conserved when whatever system you're analyzing retains the same amount of total energy for a given time interval. So, for example, in this picture, you see a man riding his bike up a hill and then riding back down. Now, say we were just analyzing from the top of the hill to the bottom, and imagine that there's no friction between his tires and the ground. Now, obviously, he needs friction between them to rotate, but just imagine that there's no energy dissipated through the friction. So, his potential energy at the top of this hill would have to equal his kinetic energy at any point going down the hill. So you take his potential energy at the top, and that would be your total energy for the system, since that's the only energy at that point. Say it's like 10 joules. That means his kinetic energy when he gets to the bottom, meaning there's no more potential energy, would have to equal 10 joules as well. So another example you can think of is a ball rolling up a ramp. The kinetic energy translational plus the kinetic rotational energy, so the total kinetic energy, has to equal the total potential energy when the ball gets to the height of the ramp. So the net work on the system is equal to 0. Alright, here's a quick review of simple harmonic motion. And looking at this picture is very similar to the problem that we'll be doing, but imagine that this is like a physical pendulum oscillating between two amplitudes. So we know that for any simple harmonic oscillator, the second derivative of its position is proportional to the negative of its position. We also know that the period for a simple harmonic oscillator is 2 pi over its rotational velocity, omega. And here are two equations we deal with when dealing with the position of a simple harmonic oscillator. X is equal to x max cosine of omega t plus the phase angle. And the same applies for theta, which is the rotational version of this equation up here, where omega is once again your rotational velocity, and x max and theta max are the amplitudes of the position. Omega is the angular velocity of an oscillator, so like the angular velocity of a pendulum, for example. T is the period of oscillation, and phi is the phase angle of oscillation. And you usually only deal with phase angles when you're given a graph. So in this problem, we will not be dealing with a phase angle. All right, here's the problem. Take a minute and look over it. All right, so for part A, the problem asks us to calculate the rotational inertia of the rod about the pivot. And this is actually pretty simple if you're using the parallel axis theorem to solve. We can say that the inertia about the center of mass of the rod. Now, for this problem, let me make two things clear. The center of mass of the rod is not at the pivot. The center of mass is at L over 2. It's directly in the middle of the rod because it's a uniform rod. The pivot is at L over 3 distance from the left side, and so these two things are not in the same spot. So the pivot is not at the center of mass, which, since we have an object rotating about an axis that is not at the center of mass, we know we can use the parallel axis theorem. Alright, so the inertia of the center of mass of this rod is 1/12 ml squared, which you can find that out either by using integral calculus or just by memorizing it. But if I showed it to you using integral calculus, then it's the same method as the next step, in which I show you how to solve the entire thing using integral calculus. So I'll just show you how to do it in the next step. I'm just assuming that you can know this from memory. And for the purpose of this problem, we're just going to multiply this equation by 3 over 3, or this fraction by 3 over 3, and we're going to say the inertia about the center of mass is equal to 3 ml squared over 36, which is the same as 1/12. Alright, the inertia about point P, which is the pivot, is the inertia of the center of mass plus the mass of the rod times the distance between the pivot and the center of mass squared. Okay, so we know that the distance of the center of mass from our reference point of the left end of the rod is L over 2, and the distance of the pivot from the left end is L over 3, which gives us a distance between them of L over 6. L over 6 squared is L squared over 36 for the d squared we need for this equation. And just plugging everything in, we see that the inertia about point P is 3 ml squared over 36 plus m times d squared, which would give you ml squared over 36. And this is just coming from this equation up here, just plugging in ICM and d squared. So this gives you a total inertia about the pivot of ml squared over 9, which is the correct answer. Now, the other way to solve this is with integral calculus, and that's what I'll be showing you right now. Alright, the first step of the integral calculus method is to go on the equation sheet and get the formula for inertia. and this is the integral of x squared dm. And we already talked about the reason why I'm calling it x squared instead of r squared like it says on the equation sheet. But you know that your two variables are different here. X is not m. X is different from m. So you need the same variable under here to successfully solve for the integral. So like I showed you in the review of integral calculus, we know that the inertia is equal to m over L times the integral of x squared dx. Okay, so for our limits of integration, this is kind of tricky to think about. You need to include the entire rod under as like in your limits of integration. So what are your limits going to be? Now, the most intuitive way I thought about this was having one end of the rod. So using our reference frame as the left end of the rod, we're going to change our reference frame here to the pivot because I think that makes it easier to separate this rod into two sections. The left side right here and the right side over here. Okay, so from the pivot, this left end of the rod is a distance of negative L over 3. And the right end of the rod is a length of 2L over 3. And so we successfully include the entire rod in our limits of integration, but we separate it into two distinct chunks, the left side and the right side from the pivot. So we set those as our limits of integration, and we use x squared dx underneath there because that's what we had in the previous step. All we've done is add limits of integration. Then we integrate using like the reverse power rule. So we know that the integral of x squared dx is going to equal x cubed over 3. We have our m over L, which was outside the integral earlier, and we have our two limits of integration to be evaluated at. And we know that this symbol means that we're going to plug in 2L over 3 for x and negative L over 3 for x and subtract them. So since this negative L over 3 is going to stay negative when it gets cubed, we can say that 2L over 3 cubed minus negative L over 3 cubed is going to be a positive. That's why this is a plus right here. So what I've done here is I've separated out the x cubed from the m over L and from this 3 in the denominator, and I've just made this constant m over 3L. Now inside our brackets, we're going to plug in our 2L over 3 for x and our negative L over 3 for x, which will give us 2L over 3 cubed plus L over 3 cubed. Solving that out, or cubing both of those, gives you 8L cubed over 27 plus L cubed over 27, which will give you 9L cubed over 27, which multiplying 9L cubed over 27 by m over 3L will give you ml squared over 9, which is the correct answer, and the same answer we got in the parallel axis theorem method. This method's a little bit more drawn out, and it takes a lot longer, so I would not recommend it for the AP exam, but it's good to know how to do because it teaches you how to think about these rods and these extended bodies in terms of integral calculus. Alright, part B. The rod is released from rest from the horizontal position above. Calculate the linear speed of the bottom end of the rod when the rod passes through the vertical. Alright, so here we have a picture of the rod horizontally before it's dropped. And we have a picture of the rod when we need to analyze the speed of the bottom of the rod. So, alright. This is how we're going to use energy conservation to solve this problem. And we know that energy is conserved because the total amount of potential energy in the system is equal to the total amount of rotational kinetic energy. There's no way for the energy to be leaving the system other than if there was like a lot of friction between the rod and the pivot, but we can just assume that the pivot and the rod are frictionless. So we're going to make the statement that the energy initial of this rod right here before it's released is equal to the final energy when we're analyzing the rod in its upright position. So we can also make the statement that the total gravitational potential energy at this position is equal to the total kinetic rotational energy at this position. And we know the formula for gravitational energy potential energy is mgh, and we know that the formula for rotational is rotational kinetic is 1/2 inertia omega squared. And the tricky part about this solution is knowing that h is the distance from the pivot to the center of mass. So if you can kind of imagine this rod, the pivot and the center of mass are about this far apart, and then when it rotates down, now the center of mass has rotated down this much. So it's moved down a total distance of whatever the distance between the pivot and the center of mass is, which we found from the previous step was L over 6. So the center of mass during this time interval that we're analyzing moves down a total of L over 6 distance. Now, of course, it moves in a circle, like a curved path, but it moves in the y dimension a distance of L over 6. Okay, so plugging in L over 6 for h, and plugging in our inertia from our previous step as ml squared over 9, we get this equation right here with our only variable, to be analyzed being omega squared. And remember from our rotational inertia or rotational motion review that the velocity at the linear velocity at any point, and we're asked to calculate the linear speed, so we know we're dealing with linear velocity and not rotational, is equal to r times omega. So omega equals v over r, and omega squared equals v squared over r squared. Now, we're going to plug in v squared over r squared for this omega squared right here, because these are equivalent. And we know that the radius of what we want to analyze the bottom of the rod, right? So we're analyzing the bottom of the rod from the pivot. Now, the pivot to the bottom of this rod is a distance of 2L over 3, so that's why we use 2L over 3 for our radius here. And r squared is 4L squared over 9. And plugging everything in gives us this equation, and the only thing we need to analyze here, well, I haven't plugged in the r squared, but I do that, and then in the next couple of steps I plug in for r squared, just to make it a little bit easier to see my variables while I'm working. So we solve this equation for v squared, and we get this 18r squared mgl over 6ml squared. And doing a bunch of canceling and plugging in our r squared that we solved for down here, we get a final answer of v equals 2 times the square root of lg over 3. And this is the correct answer from the AP exam. The only things that are kind of tricky about this are knowing what h is and knowing what r is in your equation. Just know that h is the distance that the center of mass travels downwards during the time interval. And r, since you want to analyze the speed of the bottom of the rod, you need the radius or the length from the pivot to the bottom of the rod. Alright, part C. The rod's brought to rest in this vertical position, and it then displaced a small angle or whatever, and then it starts to oscillate just much like a pendulum. Alright, so this method of solving it, which the AP exam accepts, is kind of strange because we don't really learn about the physical pendulum formula. Like, it's not on the equation sheet, and you do learn about it, but it's kind of a thing you have to memorize. You can derive it, but once you start to derive it, it starts to get into the next method of solving this, which I'll show you on the next slide. But if you memorize the formula for a physical pendulum, and this is a physical pendulum, not a simple pendulum, because we're analyzing the mass of the pendulum as well. So, you know that the physical pendulum equation for period is 2 pi times the square root of inertia over mgh. And h is the height change of the center of mass, which is the same as the last section of this problem, is L over 6. And plugging in everything and canceling will give you a total answer of 2 pi times the square root of 2L over 3g, which is the correct answer. And doing it this way is completely fine on the AP exam. If you memorized this equation for the period of a physical pendulum, you didn't even need to show how you got it. Like, you can just state that equation, plug everything in, and get the correct answer. Alright, now here's how I would have solved this problem on the AP exam. I think this is a little longer, a little bit more intuitive using your knowledge of simple harmonic motion. Alright, so we start off by saying that the net torque acting on the rod during its fall, or its rotation, is equal to its inertia times its rotational acceleration. We also know that the only torque acting on the rod is at the gravity acting on the center of mass, which will be the force of gravity, which is mg, times the height, which we've already said was the distance between the pivot and the center of mass, which is L over 6, times sine theta. Alpha, we know that alpha is equal to the second derivative of theta, or the rotational position. And alpha is also equal to the torque, or net torque, over the inertia, based on this equation up here. Okay, so we know that alpha is the second derivative of theta, and we know we can plug in our values that we get for net torque and inertia. And the reason that we say that net torque here is negative is because it really kind of doesn't matter whether you say it's negative or positive when you first think about it. But later on, there's a reason that we say that the net torque is negative. Because you could say that clockwise was the positive direction or counterclockwise was the positive direction. So you could really say that your torque is negative or positive here. But we're just going to say it's negative because it will work out better. And you can see that start to take shape because you know from simple harmonic motion that to be a simple harmonic oscillator, the second derivative of your position needs to be proportional to the negative of the position. And we use the small angle approximation of sine theta is approximately equal to theta. And here I'm just saying that h equals L over 6. But we can say that sine theta is equal to theta for very small angles. And since the problem says it is displaced slightly from this position, we can kind of assume that it's a very small angle, less than 15 degrees. So we can make the small angle approximation here. And we can replace the sine theta with just regular theta. And now we can see that the second derivative of position for this oscillator is proportional to the negative of its position. And that's one of the requirements to be a simple harmonic oscillator. Alright, so after canceling this out using algebra, the m's cancel and one of the l's cancels, 6 and 9 cancel. We get the second derivative, or d squared theta, is equal to negative 3g theta over 2l. We also know that theta is equal to theta max times the cosine of omega t plus phi, which we can replace theta max with a for amplitude. And we know that cosine, we know that there's no phase angle here, so we can just make that 0. And we say that theta is equal to a cosine omega t. And we can take this theta now and plug it into our theta from our previous equation. And we end up with this. The second derivative of theta is equal to negative 3g over 2l a cosine omega t. Alright, now we continue by saying, or here, I wrote this equation back out on this second slide here. We also know that the second derivative of position, which we take this position equation right here from the equation sheet, and we derive it 2 times using chain rule, and we get the second derivative of this position is equal to negative omega squared times a cosine omega t. We also know that the second derivative of the position is equal to negative 3g over 2l a cosine omega t from the previous slide. So we can set these two equal to each other, and the a cosine omega t's will cancel out, and we know that omega is equal to the square root of 3g over 2l, because if we cancel out these and take the square root of both sides, we'll get square root of 3g over 2l. We also know from the equation sheet that the period of a simple harmonic oscillator is 2 pi over omega. So plugging in our omega for 3g over 2l square root, we get the period of this rod as it's oscillating is 2 pi times the square root of 2l over 3g, which is the same answer we got with the physical pendulum formula and is the correct answer. Alright. Lastly, we have an incorrect approach to this problem, which is to use the equation for a simple pendulum, which you do not take into account the mass of the whole pendulum. You just take the mass of like a little bob at the end of a string, for example, where the string's mass is negligible. But since this is an extended body and not like a particle, we have to say that it's a physical pendulum, not a simple pendulum. And using this equation and using L as 2L over 3 for the L over G, we get the same answer, which is the correct answer, but no credit would be awarded for this answer on the AP exam, and they explicitly state that in the solution, because you cannot say that this rod is a simple pendulum because it's a uniform rod with a mass and a length. Alright, well, thank you for watching, and I hope you learned something from this video.